Section: Introduction. In this section, we discuss the significance of video data in research, highlighting its ability to provide richer information than text. Over the years, our focus has shifted from basic tasks like action recognition to more complex applications such as video captioning, question answering, and video generation. Despite the abundance of video content online, we face challenges related to quality and diversity. Recent efforts have aimed to improve these issues through video generation using neural models or simulations, but the goal often remains to replicate real-world scenes, which limits creativity and application. We introduce the idea of impossible videos, which depict scenarios that cannot exist in reality. We believe these videos can serve as a valuable testing ground for video models. Unlike traditional data, impossible videos require models to learn and reason rather than just recall real-world information. We categorize current video models into two main types: understanding and generation. Our work seeks to explore the intersection of these models by addressing two key questions. First, can modern video generation models create impossible content based on text prompts? The focus in video generation has shifted from basic quality to more complex semantic aspects, with state-of-the-art models acting as world simulators. We challenge these models to generate impossible videos while adhering to the prompts. Second, we ask if current video understanding models can effectively interpret impossible videos. Advanced models, particularly video large language models, video LLMs, have shown strong performance on real-world video benchmarks. However, impossible videos present unique challenges in reasoning about time and knowledge of the world. To tackle this, we propose a benchmark called IPV-BENCH, dedicated to impossible videos. This is the first effort of its kind, and we start by creating a detailed taxonomy that covers various aspects of impossible videos, including those that violate physical, biological, geographical, and social laws. From this taxonomy, we develop IPV-TXT, a suite of 260 text prompts, and IPV-VID, a collection of 902 high-quality videos, all organized to reflect the taxonomy and focusing on temporal dynamics. Using this benchmark, we evaluate mainstream video understanding and generation models, finding that many struggle with impossible videos. Our analysis reveals limitations and suggests future research directions. We plan to make our data publicly available to encourage further exploration. In summary, our contributions include the identification and investigation of impossible videos, the creation of the IPV-BENCH benchmark, and a comprehensive evaluation of existing video models, highlighting their limitations and potential future paths. In the related work section, we evaluate video models in two main areas: understanding and generation. We present a comparison of IPV-BENCH with existing benchmarks, outlining their differences and objectives. Video understanding remains a key challenge, involving tasks like action recognition and captioning. Video LLMs utilize language to perform various video tasks, often extending from models designed for images. Popular benchmarks assess models on diverse tasks and scenarios, but none focus specifically on impossible videos, which are essential for evaluating model robustness and reasoning. Video generation has gained significant attention, particularly in text-to-video tasks. Notable models include stable video diffusion and others, with challenges centered on achieving high visual quality. Recent benchmarks have begun to evaluate models on their ability to generate physically plausible videos. However, the generation of impossible scenes, which is crucial for creativity in fields like film and advertising, has not been systematically studied. Section Summary. In this section, we introduce the concept of impossible videos, which depict counterfactual scenes that challenge current video understanding and generation models. We present IPV-BENCH, a benchmark designed to evaluate these models' capabilities in handling such content, highlighting their limitations and paving the way for future research in this unexplored area. Section: IPV-BENCH. In this section, we develop a classification system that organizes different types of impossible scenes. This system lays the groundwork for two key parts of our benchmark. First, IPV-TXT, which is a collection of high-quality text prompts that describe impossible scenes, and second, IPV-VID, a selection of high-quality videos showing these impossible scenes, each with annotations. Our taxonomy is divided into 4 main categories: physical laws, biological laws, geographical laws, and social laws. Each of these categories has subcategories, creating a detailed structure. Our IPV-TXT benchmark includes 260 text prompts that illustrate various unusual scenarios. The physical laws category includes 6 common laws, such as mechanics and conservation laws. For instance, one prompt describes a scene where a person pours milk into a glass already half full, but the amount of milk doesn't change, violating the conservation of mass. In the biological laws category, we have 3 subcategories. The first, biological capability, includes scenes that exceed what humans or animals can do, like a person flying by flapping their arms. The second, morphology, features impossible body compositions, such as a horse growing from 4 legs to 8. The third, anthropomorphism, describes non-living objects acting like humans, like a talking fried egg. The geographical laws category addresses impossible natural phenomena, such as a mountain flattening into a plateau while keeping its trees intact. The social laws category includes 3 types of unusual scenes: common sense, which violates daily routines; magical effects, which involve creative, unexplainable events; and historical anomalies, which show impossible interactions between people from different time periods, like Albert Einstein meeting Donald Trump. To create our taxonomy and IPV-TXT benchmark, we follow a structured framework. First, we initialize the taxonomy by reviewing literature and using large language models for insights. We then refine the taxonomy and prompts through an iterative process, adjusting the structure as needed based on new prompts. We also use multiple language models to generate diverse examples. To enhance our taxonomy, we gather outlier samples through crowdsourcing, collecting data from participants with various backgrounds. We ensure the authenticity of the data by specifying that language models cannot be used in the questionnaire. We review the prompts for clarity, accessibility, relevance, and visualizability, making necessary revisions. Finally, we enhance the linguistic quality of the prompts to make them suitable for video generation models. This process results in a comprehensive taxonomy and prompt suite that can assess the ability of models to generate impossible videos, advancing research in this area. Section Summary. In this section, we develop a comprehensive taxonomy categorizing impossible scenes into 4 major categories: physical, biological, geographical, and social laws, which informs our IPV-TXT benchmark of 260 high-quality text prompts and IPV-VID videos. Our iterative methodology involves refining the taxonomy and prompts through literature review, LLM insights, crowdsourcing, and quality control to create a robust framework for assessing T2V models' capabilities in generating impossible videos. Section: IPV-VID. In this section, we introduce IPV-VID, a new video benchmark aimed at evaluating how well popular video LLMs can understand temporal dynamics and world knowledge through impossible videos. IPV-VID is organized based on a recognized classification system and focuses on identifying temporal anomalies, like unusual movements and scene changes, which are hard to detect from single frames. For video collection, we first generate a wide range of videos using 10 advanced text-to-video models, including both open-source and closed-source options. We use a set of 260 high-quality text prompts from the IPV-TXT suite to create a total of 2,600 synthetic videos. To broaden our dataset, we also gather videos from the internet, particularly from community sites related to commercial video generation models and user-shared content on Twitter, ensuring these videos depict impossible scenarios. From these sources, we collect 155 videos. To balance our benchmark and reduce evaluation bias, we include real-world videos. We use OpenVid as our main source and apply the clip model to find videos that match the content of our AI-generated videos. We filter these videos based on length, aspect ratio, and aesthetic quality, excluding those with cartoon visuals, logos, or subtitles, resulting in 650 real-world videos. For human annotation, we first filter the videos to ensure they depict high-quality impossible or counterfactual scenes. We create a custom annotation tool for this process. Our criteria focus on two main aspects: visual quality, where we exclude low-quality videos, and semantic plausibility, where we keep videos that show impossible content. We then perform detailed annotation on the selected videos, labeling them for spatial or temporal anomalies, assigning taxonomy categories, and providing brief explanations of the impossible phenomena. In evaluating impossible video generation, we assess various mainstream video generation models. We generate videos using the IPV-TXT prompts and have human annotators label them for visual quality and adherence to the impossible prompts. We introduce the IPV score, which measures the percentage of videos that are both high quality and accurately represent the impossible events described. We also propose an automated evaluation method to further assess the model's capabilities, with detailed analysis available in the appendix. Section Summary. In this section, we introduce IPV-VID, a novel video benchmark designed to evaluate video LLMs on their ability to reason about temporal dynamics and world knowledge through impossible videos. We detail the collection of synthetic, web, and real-world videos, emphasizing high visual quality and low semantic plausibility, and outline our evaluation process using the IPV score metric to assess the performance of various video generation models. Section: Results and Analysis. In this section, we explore whether today's video generation models can effectively create impossible video content based on prompts. Our findings indicate that the best model, Mochi 1, only generates high-quality impossible videos in about 37% of cases, while other models perform even worse. This suggests that current models are still not meeting the standards for generating high-quality impossible videos. We notice an imbalance in capabilities between visual quality and prompt adherence. For example, Luma excels in visual quality but struggles with following prompts, while Mochi 1 shows better prompt following abilities, even outperforming some proprietary models. Ideally, a model should perform well in both areas, which we measure using our IPV score metric. We identify two main challenges in generating impossible videos. First, impossible prompts can lead to low visual quality, as the unusual nature of these prompts often results in visual errors or failures. This is likely because they fall outside the model's training data. Second, a strict focus on physical laws can limit the model's creativity, leading to videos that accurately reflect the prompt's semantic elements but fail to show the impossible aspects, instead depicting normal scenes. We evaluate various popular video LLMs, both open source and proprietary, through 3 progressively difficult tasks to assess their capabilities in understanding impossible videos. In the judgment task, most models perform similarly, with Qwen 2VL achieving the highest accuracy. However, we observe some models show bias, often answering yes or no predominantly. To address this, we also report F1 scores, with video LLAVA performing the best. In the multi-choice task, performance varies significantly. LLAVA next leads with an accuracy of 86.4%, while video LLAVA scores only 26.8%, close to random guessing. Most open-source models have considerable room for improvement. The open-ended QA task is conceptually simpler but practically challenging, with many models struggling to identify counterfactual phenomena in videos. LLAVA next performs well, and GPT-4o shows strong visual understanding. Overall, our results suggest that most models have difficulty comprehending impossible videos, indicating a promising area for future research. We find that proprietary models generally outperform open-source ones, but their ability to identify impossible videos independently is still lacking. We also observe unbalanced capabilities across different tasks and domains. The physical domain is particularly challenging, with most models scoring low. We hypothesize that this domain requires more complex reasoning. Performance on the MCQA and OpenQA tasks is correlated, but the judgment task stands apart. To determine what makes a good model for understanding impossible videos, we identify two key factors: temporal dynamic reasoning and world knowledge reasoning. For instance, recognizing an impossible event often requires analyzing multiple frames, while understanding certain scenarios, like snowing in Singapore, relies on world knowledge. We find that temporal reasoning is particularly challenging for current models, as evidenced by lower scores on temporal-focused videos compared to spatial ones. Interestingly, top-performing models are image-based, and even GPT-4o, which operates at a lower frame rate, shows strong performance. This suggests that enhancing temporal reasoning capabilities, rather than merely increasing context, may be crucial for understanding impossible videos.